Hey class, it's Mr. Ng. In this video, I want to go through our lesson on Punnett squares all over again. So, in case you didn't get it, you can watch this video. Hopefully, this will help you out. Let's get started. So, we have a problem here. In humans, widow's peak is the dominant trait. I misspelled dominant. My apologies. This is a widow's peak right here. On Paul Ryan, he has a widow's peak. Perform a cross between two individuals who are heterozygote for widow's peak. So, first, let's set up our alleles. So because widow's peak is a trait, we're going to use the first letter. So we're going to say that big W is the dominant trait, right? That's how we do things. The capital letter is dominant, and that means that big W means you got a widow's peak, right? Or that's the allele that codes for widow's peak. That means little w is going to be no widow's peak. Seems simple enough, right? I'm just kind of going with what the problem told me. It said that widow's peak is dominant, right? So big W becomes widow's peak. The part that's a little tricky that some of us have been struggling with is how do we set this thing up? Well, the clue that we have about the parents is that both parents are heterozygote. And if you remember, hetero means different, like heterogeneous means like different, right? So that means these individuals have both alleles. That means both parents will be big W and then little w, big W and then little w, right? And then to fill it in, this is what I'm going to do, right? This box will have big W, big W. This box will have big W, big W, little w, and then little w, right? What does this Punnett square mean? Well, it means out here are the parents, and the parents have two alleles, the big W allele and the little w allele, and they're going to separate them out and kind of combine them randomly. And in here, these are the possible offspring. It does not mean that these parents made exactly 4 offspring, but these are the 4 possible combinations of their alleles. So let's report out the genotypes and then the phenotypes. The genotypes refers to what are the possible genetic combinations for the kids. And there are 3 possible genotypes: big W, big W, big W, little w, little w, little w, right? And if you look over here, we got 1 out of the 4 is big W, little w, 1 out of the 4. And then 2 of them, this guy here and this guy there, are going to be big W, little w. So this is 2 out of 4. And then finally 1 out of 4 here. All right, those are the genotypes. A 1 to 2 to 1 ratio for the genotypes, right? And if you're wondering how I got that, I just used the numerators here and I put them into that little order, all right? So what are the phenotypes? What will we see, right? How many of these kids might have a widow's peak? Well, the 2 phenotypes here is to have a widow's peak or no widow's peak. Right? And then these 2 genotypes will code for widow's peak, right? Meaning 1/4 and 2/4. If you add those together, that means 3/4 of the possibilities will make a widow's peak, while 1/4, this double recessive, means no widow's peak, right? Because it's a recessive allele. And then to rewrite it, we take this 1, we take this 3. It's a 3 to 1 ratio of having a widow's peak. Hope that helps. Let's do another one to clarify some things. Dwarfism is a dominant trait, right? And here, look at this, Peter Dinklage being his dwarfy self, right? If a heterozygous dwarf marries a non-carrier, what are the chances that their child will be a dwarf? So, dwarfism is dominant. I know that seems a little strange because there are so few dwarves out there, but just because you're a dominant allele doesn't mean that you're also the most common allele. That's a very common misconception. So let's let big D equals dwarfism, right? This is the allele for dwarfism. So that means little d means not a dwarf. Fine. Right. I've noticed that a couple of you guys like to skip this step, but I still recommend that you kind of clarify it just because sometimes we make assumptions as to what's dominant and what's not. This is just a good way to remind ourselves as to what's dominant and what's not. And that obviously has bearing as to how the phenotypes turn out, right? So let's figure out what the parents are. One parent is a heterozygote dwarf. Heterozygote means big D, little d. and then a non-carrier. That means this person does not have a single allele for being a dwarf. They don't carry a single allele for being a dwarf. That means they don't have a big D in their genotype. Then they must be little d, right? Does that make sense? So one parent is big D, little d. The other is little d, d. Let's fill in the boxes. This becomes big D, little d, little d, little d, big D, little d, little d, right? And if you notice, I always put the dominant allele first. That's just the formality of it. What's our genotype? Well, there's only two possible genotypes, big D, and then little d. And then both of these occur 2 out of 4 times, right? Look, 2 out of the entire 4. That means that it is a 2 to 2 ratio. And you could reduce it to just a 1 to 1 ratio. That's pretty good, right? And then the phenotype, well, who's going to be a dwarf? These guys would be dwarfs, right? Anything with a big D in it will be a dwarf, and these guys here will not be dwarfs. So it'll be dwarf versus not a dwarf, not a little person, right? And then this will be 2 out of 4, 2 out of 4, or a 1 to 1 ratio again. Done. Hope we're getting the hang of it. Let's do one more simple one like this. Albinism is a recessive trait. This is different from the last one, right? The last one, dwarfism, is a dominant trait. If a carrier for albinism marries a non-carrier, what are the chances that the offspring will inherit albinism? All right, albinism. So albinism is recessive, so let little a become albinism. Albino. Right, that means big A means not an albino. All right. So let's set up our box again. Let's figure out the parents. A carrier for albinism. A carrier is an individual that has the affected allele but does not exhibit the traits. Someone who holds the gene for albinism but is not an albino. There's only one way for this to occur, and that's to have big A, little a. Right? The little a means you have the allele for albinism, but because the big A is here, you don't have albinism. So you just kind of carry the allele in you. So one parent is big A, little a. A non-carrier means that you don't have little a at all. There's no part of you that has little a. That means you must be big A, big A. Big A, big A. So this becomes easy. Big A, big A. Big A, little a. Big A, little a. Done, done, done. So let's go with the genotypes again. Hope this is getting easy. Right? Only two possible genotypes. These guys here, big A, big A. And then these guys here, big A, little a. Right? And then we're just counting boxes. 2 out of the 4 will be big A, big A. 2 out of 4 will be big A, little a. So that means it's a 2 to 2 ratio, or let's reduce it 1 to 1 ratio for big A, big A to big A, little a. And then if we want to do the phenotypes, let's see. These guys will not be an albino. These guys will also not be an albino, right? 100% will not be albinos. 100% exhibiting, melanism. Look at this cute little hedgehog. Look at evil. All right, so that's pretty easy. Hope you got the hang of it. Let's move on to some different types of problems. Let's talk about codominance and incomplete dominance. I know we've been harping on how Mendel discovered the law of dominance, how one allele is more dominant than the other, but that's actually very rare. Mendel was very lucky to find those few traits that had the very simple dominant and recessive types of inheritance. Instead, most inheritance is kind of complicated, where most of your traits take several genes and most of your genes exhibit several traits. So it's kind of a mishmash. And here, many traits do kind of mix together, right, in a form that's either codominant or incompletely dominant. Codominant means both show, so we're talking about like spots or stripes, okay? And here we use capital letters like big A and big B. And then for incomplete dominance, these things are going to be mixed together, so nothing really shows. So this is like a blended color typically, right? So then for here we use lowercase letters. And because there's going to be two different colors or whatever, two different traits, we're going to use two different letters this time instead of the same letter. It'll be more clear once I do an example, okay? So let's do an example about the color of roses. The color of roses are incompletely dominant, right? Meaning there's no red rose or white rose when they cross, they make a pink rose, right? Perform a cross between a red flower and a white flower. So let's establish our alleles. Let's let R, see, and look, I did a lowercase because you don't see a red show up. It's incompletely dominant. Let little r become red. Let little w become white. And then for pink, pink is going to be RW. That's going to become pink, okay? So let's do a cross between a red flower. A red flower, well, there's only three possible combinations, RR, RW, or WW, right? RW is pink, WW is going to be white, so RR must be red. So to make a red flower, we're going to do RR. And a white flower, that must be WW. So everybody's going to be RW. You know, the codominant problems are a little bit easier because you could do the phenotypes and genotypes at the same time. So let's do the phenotype and the genotypes at the same time. So they're going to be 100% RW, or we know that RW means pink. 100% of these flowers or these offspring are going to be pink, right? Done. Let's do another one. This is an example of codominance, meaning both colors show up. Look, both the white and the brown shows up in a bunch of spots. In this case, in a Rowan cow. So let's let big B equal a brown and brown. Let big W equal white pigment, and then BW, that's Rowan. Right? That's the mix. Right, so perform a cross between a Rowan cow and a brown cow. Well, seems easy enough. Rowan is big B, big W. And a brown cow is big B, big B. So this becomes big B, big B, big B, big B, big B, W, W, B, and W. So half brown, half Rowan. So let's go with our geno/phenotypes. Right? So we got BW, which is basically Rowan, right? That's going to be 2 out of the 4. And then big B and big B, that's basically brown. That's also going to be 2 out of 4, meaning a 1-to-1 ratio of Rowan to brown. Good? Okay. Last type. These guys get a little bit complicated. I need to also teach you about X-linked traits. X-linked traits sit on the X chromosome. So before we go any further, let's do some real basic stuff. You need to know about your sex chromosomes. Girls are XX, boys are XY, right? And then when we do these crosses, we're gonna always attune to their genders, to their sexes. Okay, so let's just do an example. Hemophilia is an X-linked disease. Perform a cross between a male hemophiliac and a female carrier. So there's a lot of things to talk about here, okay? So this is about hemophilia. This is a disease where the blood doesn't clot very well. And I have a picture of the Russian royal family because they were known to have a lot of hemophilia because there was a lot of marrying amongst princes and princesses, so that trait kind of recurred quite often. So perform a cross between a male hemophiliac and a female carrier. So how do we do this? Well, XH is going to be hemophilia, okay? How did I establish this? Well, we know that it's an X-linked disease, so it sits on the X, and then when it's sick, we put a little H there. A normal X is going to be normal X, and then of course Y is a normal Y. Is there such a thing as a YH? No, no such thing, because hemophilia is X-linked, right? X-linked, not Y-linked. It makes no sense. So let's do our cross. So let's do the girl and then the boy. Makes sense. And then a male hemophiliac. A male hemophiliac. The male hemophiliac, I'll put a little H right here, right? And then the female carrier has a H right here, right? A carrier meaning one of the X's is sick and the other one is fine, a carrier. So before going further, just so you know, this girl up here, this female, does not exhibit hemophilia. All right, she's a carrier. But this boy with just one sick X, this boy is sick, or this man, or this person right here, right? So which is why hemophilia kind of exhibits itself far more likely in males, because females have an extra X to kind of buffer the phenotype. Now let's just do this cross. X, H, X, H, X, H, Y, X, H, X, X, Y. So here we have all four genotypes. So one of them is going to be XHXH. This person is sick and female, right? Now, you know what? I'm just going to start doing this symbol. This symbol is the mirror of Venus, so that's a female. We also have an XHX. This is a carrier female. We also have an XHY. This is a sick male. Sick. There you go. And male, I'm going to do this symbol. This is the spear of Aries, all right, or the spear of Mars, or masculine, right? And then finally, XY. This is going to be a normal, healthy male. Okay, and all of them is a 1 to 1 to 1 ratio, right? 1 to 1 to 1 to 1. All right, so there's a quarter of a chance for any of these genotypes and phenotypes to occur, right? Here are my genotypes. Here are my phenotypes. Okay, let's do one more cross. Red-green color blindness is also an X-linked trait. Perform a cross between a color-seeing male, okay, and a carrier female. All right, and here I have a picture as to what these people might experience when they look at red and green dots, right? They don't really see them very well. Again, this is something that occurs way more in males. It's very rare for females to have this occur, just because they have two X's that need to be sick, right? So how do we, let's see, colorblind. Let's do a C. So XC is the affected X gene, right? X chromosome, affected X. Then this is the normal X, and then this is the normal Y, right? Normal X, normal Y. All right, so let's do a cross between a boy and a girl, meaning XX and XY. We always start there with these X-linked traits because you have to have an XX and an XY to make a baby. And then let's see, perform a cross between a color-seeing male. A color-seeing male means that this must be healthy. We put a little C there, right? If we put a C here, then this male will be colorblind. So we gotta not have a C there, okay? And then a carrier female, that means one of these X's has the allele, not two, because then the female would also be colorblind. So let's do XCX, XCY, XX, XY. So looks like we have almost every combination. We have XX, which is going to be a normal female. We have XY, which is a normal male. We have an XCX, which is a carrier, right? Meaning this female can see colors, can see red and green, but might have a son that won't. And finally, the XCY, that is a colorblind male. All right. As you can see, these X-linked traits affect males more often just because they only have one X, and if that X is sick, well, then they get that phenotype. Females, however, need two sick X's. And that is basically it. I know this was a very long video, so thank you very much for watching. I hope that helps out. Feel free to rewatch the segments that you know you need to buff up on. And thank you very much. Have I don't have a good day, I guess. I don't know. It's a daytime. Bye bye.